Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the topic pipeline and Arithmetic pipeline. So, we are discussing about the concept of pipeline. So, pipeline is a technique of decomposing a sequential process into sub operations. So, the pipeline is a technique. So, using this technique, we are decomposing a sequential process into sub operations, and with each sub process is being executed in a special dedicated segment that operates concurrently with all other segments. So that is called pipeline. So mainly this pipeline concept we are using in multiprocessor systems. So multiprocessor system means the system which is having more than one processor. So that in a multiprocessor system, the task will be shared by all the CPUs which are available in the system. So suppose if the system is having three CPUs, then the task will be shared by the all the three CPUs, so that the efficiency and the performance of the system will be improved. So that is a use of the pipelining. So in this pipelining concept, in the pipeline concept, it will execute two or more instructions simultaneously. But if you consider a sequential approach, so after completing one instruction, then the second instruction will be executed, then third. So like that, all the instructions of the program will be executed in a sequential manner. But in the pipeline concept, while the first instruction is executing, the second instruction will be fetched from the memory. While the second instruction is fetching from the suppose actually every instruction, it is having three phases. One is the fetch, decode, and execute. So these are the three phases of the instruction. So every instruction, it has to undergo these three phases: fetch, decode, and execute. Suppose if the first instruction is fetched from the memory, and then the second, then it will undergo a decoding phase. So while the first instruction is in decoding phase, then the second instruction will be fetched from the memory simultaneously. So this decoding of the first instruction and fetching of the second instruction will happen at a time. That means simultaneously. So in this way, the performance of the system will be improved by executing multiple instructions concurrently. So see here. So in the pipeline concept, the process. So the process P. Let us assume we have a sequential process. So we are assuming P. So this process, sequential process, we are dividing into a sub operations. So like some P1, P2, P3, and so on, Pn. So this process, sequential process, we are dividing into sub operations, which each sub process being executed in a special dedicated segment. So this process P1, it will be executed in one segment. P2 will be executed in another segment. So P3 will be in another segment. So like that, all that segments S1, S2, S3, and so on. So all these segments are that are operated concurrently. That means at a time all that will be operated, so that the final task will be performed. So each segment performs partial processing dictated by the way the task is partitioned. So the result to obtain from the computation in each segment is transferred to the next segment in pipeline. So if you consider the example of the pipeline processing, so this is a diagram, so which gives the example of the pipeline processing. So how the multiple processes will be executed. So see here. So suppose if you consider a process A suffix I into BI plus CI. So let us assume this is a one process. So this process it will divide into a multiple sub operations. So multiplication. So multiplication is one operation, and addition is some other operation. So like that. So these all the so entire the process it will be divided into a sub operations, and these sub operations are performed in dedicated segments, and all the dedicated segments are running concurrently, so that the final output can be obtained. Okay, so see here. So here this is a AI. Okay, this is a BI. So here where I value is from 1 to 7. So where I value is equal to 1 to 7. So AI, BI, and here it is a CI. So total here we are using three segments. Three segments. So this is a segment 1, this is segment 2, and this is a segment 3. So total here we are using three segments. Okay. So the S1, the segment 1, it consists of the registers R1 and R2. And similarly, the segment S2, it consists of the registers R3 and R4. So see here. So here all these. So final the output of this process can be obtained by executing this all the segments S1, S2, S3 by performing concurrently. So at a time. So at a time all the segments will be performed, so that the final result will be obtained. So the final result is obtained after the data have passed through all the segments. So this whenever this input data it is passed through all the segments, then the final result will be obtained. So you can understand in a better way in the further slides. So each segment consists of an input register followed by an combinational circuit. So see here. So this is a S1. So this S1 it consists of an input register and followed by a combinational circuit. So here we are using different combinational circuits like multiplier, adder. So these are the combinational circuits. So combinational logic circuits are designed using the basic logic gates like AND, OR, XOR. So these are the combinational circuits. Okay. So see, a clock is applied to all the registers after enough time has elapsed to perform all segment activity. So here we are applying a clock to the all the registers which are available in the circuit. So register is nothing but a group of flip-flops. So using that register, we can store some information or the data inside the register. Okay, so the information flows through the pipeline one step at a time. So the information it will pass through the registers one step at a time. So for one clock cycle, one step data flow will takes place. So here the example is AI into plus CI. So this is an expression. So this is one processor. So here the I value for I is equal to 1 to 7. 1 to 7. So that means here, see, the sub operations performed in each segment. So this entire process, it will be performed in three segments. So that are called segment 1, segment 2 and segment 3. So these are the three segments. So during segment 1, so what will happen? So during segment 1, so see here, okay, so this is a AI, this is a BI and this is a CI. So during segment 1, the AI value will be loaded into R1 register and BI value will be loaded into the R2 register. So this is the operation performed during the segment 1. And during segment 2, so in segment 2, segment 2. So okay, so after loading the AI and BI values into the R1 and R2 registers, then we are performing a multiplication. So here you can see, so it is a multiplication. So we are performing multiplication using a multiplier, a multiplier. So during S2, so this is a segment 1, this is segment 2, and this is a segment 3. So during second segment, the multiplier output will be loaded into the register R3. So this one, and the CI value, the CI value will be loaded into the R4 register. So during the second segment. So after that, so once we have finished the multiplication of the AI and BI, then we will okay. So see, we have performed the multiplication. After that, we need to perform the addition. So we have a result. So R3, it contains the result of the multiplication. So it contains the result of the multiplication. That means AI into BI. So the result is stored in the R3 register. Now we are going to add the contents of the R3 register with the contents of the R4 register. Okay, so we are adding using a adder. We are adding these two values. The contents of the R3 is added with the contents of the R4 using a adder. So after adding, okay, so that means see here. So R3 contents are added with R4, and that result will be stored in the R5 register. So that will takes place during the segment 3. So in segment 3, the contents of R3 plus R4 stored, the contents of R3 plus R4 will be loaded into the register R5. Okay, so these are the various sub operations performed in different segments. So by executing all these segments concurrently, then the final result of the operation will be obtained. So the output of the final output is this expression, AI into BI plus CI. Okay. So see here. So how we can get the final output. So see here. So the table which shows the first column is a clock pulse number, because based on the clock pulse only the register will work. And segment 1. So total we have 3 segments: segment 1, segment 2, and segment 3. So already we know the segment 1, it consists of the registers R1 and R2. So R1, R2 will be available in segment 1. And segment 2, it consists of R3 and R4 registers. And segment 3, it consists of R5 register. Okay. Now coming to the operation. First, during the first clock pulse. So when the first clock pulse is applied, okay. So see here. So already we know what is I value. I value will be from 1 to 7. So 1 to 7. That means when I is equal to 1. When I is equal to 1. So that means, see, when I is equal to 1, A1, B1, C1. So this A1 during first clock cycle, the A1 will be loaded into R1, and similarly B1 will be loaded into R2. So that A1 will be stored in R1 register, B1 will be stored in the R2 register. So during that first clock cycle, in the remaining segments, no operation will be performed. So that means this dash. So that means it represents no operation. Okay. After that, if you apply one more clock pulse, that means during the second clock cycle, then see So that means now the I value will be I is equal to 2. So that means here it is A2, B2, okay, A2, B2. Okay. So now see here, when you apply a second clock pulse, this A2 will be loaded into R1 and B2 will be loaded into the R2. But previously R1 in R1 A1 is there, in R2 B1 is there. So that multiplication will be performed and that multiplication result will be stored in the R3. So in R3 it contains A1 multiply with B1. So that's why see. So in segment 2 in R3 register it contains A1 into B1. And similarly the C1 value will be loaded into R4. So C1 value will be loaded into R4 register. And A2 will be loaded into R1 and B2 will be loaded into the R2. And during the in third segment nothing will take place. Okay. And if you apply a third clock pulse, what will happen? So if you apply a third clock pulse, then A3 now I is equal to 3, A3 B3, now C2. Okay, so A3 will be loaded into the R1, B3 will be loaded into the R2, B3 will be loaded into R2, so B3 is stored in R2. Okay, so now previously here it will be in A2, B2. Now this multiplication. So in R3, what is there? In R3, we have a multiplication result. So that multiplication result, it is added with the contents of the R4 register. So R4 register, it is having C1 previously. Okay, C1. So now in the during the third clock cycle, this multiplication result and the C1 will be gets added, so that the final output will be A1 into B1 plus C1. So that is the result will be stored in the R5. So this is a R5. So the register R5, it contains A1 multiplication with B1 plus C1. Okay. And segment 2, it contains A2 multiply with B2. And R4 register, it contains C2. So like that, all the input data will be loaded into the corresponding registers. Okay. So by the time when you apply a clock pulse number 9, so you will get the final output. So the final output is A7 plus B7 plus C7. So this is our final result. Okay, so that means here total we require 9 clock pulses in order to get the final process output. Okay, so in this way the contents of the registers will be stored in a pipelining process. And any operation that can be decomposed into sequence of sub-operations of about the same complexity can be implemented by a pipeline processor. The technique is efficient for those applications that need to repeat the same task many times with the different sets of the data. So this type of operation, it will be useful when we are performing the same task, when we are repeating the same task many times, several times on the different sets of the data. And a task is the total operation performed going through all the segments of the pipeline. The general structure of a 4-segment pipeline is shown in figure. So this is a 4-segment pipeline. So previously we have seen a 3-segment pipeline concept. So that means here there we have only 3 segments: segment 1, segment 2, and segment 3. So here 4 segments. So we have 4 segments: segment 1, segment 2, segment 3, and segment 4. So the output of every segment, it will be loaded into the corresponding registers, and all the registers simultaneously we have applied a clock. So based on that clock, that particular operation will be performed, shifting of data from one register to the another register. So that will take place. And coming to the arithmetic pipeline. So arithmetic pipeline. So already we have seen what is the pipeline. And this pipeline concept, especially this arithmetic pipeline. So arithmetic pipeline, especially we are using where the fast computers, where the fast, that means the speed is required. There we are using this arithmetic pipeline. That means by using this arithmetic pipeline, then the speed of the system will be improved. Okay, so the pipeline arithmetic units are usually found in high-speed computers, and these arithmetic pipelines are constructed for simple fixed point numbers and floating point arithmetic operations. So for these two operations, then we can use this arithmetic pipeline. One is for fixed point operations, and the second one is the floating point arithmetic operations. So already we know the arithmetic operations. So arithmetic operations means we have various arithmetic operations. Okay, so that are addition, subtraction, multiplication, division. So like that, these are the different arithmetic operations. So all that arithmetic operations we can perform on the fixed point numbers as well as floating point numbers. So to understand the concept of arithmetic pipeline in a more convenient way, let us consider an example of pipelining unit for floating point addition and subtraction. So in order to understand in a better way, we have considered an example of arithmetic addition and subtraction. So in order to understand this, consider a floating point number. Floating point numbers. So we have a two floating point numbers. One is the x and another one is a y. So x and y are the two floating point number. So already we know the floating point number, it is having, it consists of two values. One is the mantissa, and another one is a exponent. So using these two, a floating, we can represent the floating point number. Okay. So here, so the floating point number we can represent like this. So x is equal to a into 2 power a. 2 power a. So here the base we have taken 2. So the base we can represent with either 2 or 10. We can consider. Okay. So here the capital A is it is a mantissa of the number x, floating point number x, and similarly small a is it is an exponent of the floating point number x. Similarly, we have another floating point number, that is y, and the capital B is it is a mantissa of the second floating point number, that is y, and small b is it is an exponent of the second floating point number y. Okay. So already we have seen capital A, capital B are it represents mantissa, and small a, small b, it represents the exponents of the numbers. Okay. So the combined operation of the floating point addition and subtraction is divided into 4 segments. So here, what is the operation? So already we have seen pipelining. So pipelining is a technique of decomposing the process, sequential process, into sub-operations. So that means here, what is the sequential operation? So sequential operation is addition and subtraction. So this addition and subtraction operation will be performed by dividing this process into sub-operations, and that sub-operations will be will be operated in a segments. So here total, in order to perform this addition and subtraction, so total we require 4 segments. So by executing all these 4 segments concurrently, then the final addition and subtraction will be performed. So each segment contains the corresponding sub-operation to be performed in the given pipeline. So total this floating point addition and subtraction algorithm, it is divided into 4 segments. So the first segment operation is comparing. So the first segment it will compare. So what it will compare? It will compare the exponents by subtraction. So during the first segment, the subtraction operation will be performed. So comparing. So comparing of exponents. So how we are comparing the exponents? By performing the subtraction. Suppose if one number is having the power 10 power 3 and another number, another floating point number, it is having the exponent 2. Okay, so comparison. So 3, the exponent of one number, we are comparing with the exponent of the another number. So that means how we are comparing? So 3 minus 2. So that means 1. So there is a difference in the exponents. That is 1. So in this way, we are comparing the exponents. And second one is align the matrices. Align the matrices. So if there is any differences in their exponents, then we have to align the matrices. After aligning the matrices, then we have to add or subtract the matrices. So that this addition or subtraction of the matrices will performed during the segment 3. So this is segment 1, segment 2, segment 3, and the last segment is segment 4. So in segment 4, the normalization of the result will be takes place. Okay, so we will see what is normalization in further slides. So this is a block diagram. It represents the sub-operations performed in each segment of the pipeline. So already we know we have 4 segments. Segment 1, 2, 3, 4. Here, every floating point number, it can be represented with a matrice and exponents. Using these 2 values, we can represent the floating point number. So, see here. So, what is the first? So, during segment 1, what operation we are performing? Compare. Comparing the exponents by subtraction. So first we are comparing the exponents. What is the exponent of the first number? Small a. What is the exponent of the second number? Small b. So we are comparing these 2. So first these 2 exponents will be stored in a register. Stored in a register called R. After that are applying to the segment 1 in order to compare. So we are comparing the exponents by subtraction. So what are the numbers we have considered? So we have considered the numbers x is equal to this one 0.9200 into 10 power 3 and y is equal to 0.8304 into 10 power 2. So the exponent of the first number is 3, exponent of the second number is 2. So that means 3 minus 2. So 3 minus 2. So that is equal to 1. So there is a difference. So there is a difference in their exponent values. Okay. So suppose if there is any differences, then what is the second step? We need to align the matrices. So this alignment of matrices takes place during segment 2. So that's why during the segment 2, the alignment of matrices will be takes place. Okay, and also when we are doing alignment of the matrices, then we have to choose the lowest exponent value. So here, out of the 2 numbers, the first number is having the power of 3 and the second number having the power of 2. So that's why we have to choose the second number to perform the alignment of the matrices. Okay. So after performing alignment of matrices, then we have to add or subtract the matrices. Okay. So either we can perform either addition operation or the subtraction operation. So now in this case, suppose if you consider a addition operation, so then the addition operation will be performed during the segment 3. Okay, so here in the during segment 3, so in the exponents nothing will be there, nothing operation will be there, because in the exponents we are not doing, only we are adding the matrices. So that will be takes place in the segment 3. After adding or subtracting the matrices, then the last step is the normalization. So normalizing the result. So that will be takes place in the segment 4. So when we are doing the normalization of the result, then we have to adjust the exponent. Okay. So finally we will get the result, and that will be stored in the register R. So this is the block diagram. It represents how various sub operations will be performed in each segment. So this you can better understand with one example. Okay. So already we know we have 4 segments. During the first segment, the comparison will be takes place. Okay. So we have a number x and y. Okay. So the exponents are compared by subtracting them to determine their difference. The larger exponent is chosen as the exponent of the result. So always the larger exponent value will be chosen as the resultant exponent. So the difference of the exponents is 3 minus 2. So that means 3 minus 2, that is equal to 1. It determines how many times the matrices are associated with a smaller exponent must be shifted to the right. And coming to the second segment, so second segment is a alignment of matrices. So this fractional part, it is called matrix. So alignmenting the matrix. So what is the second number? So second number is y is equal to 0.8304 into 10 power 2. So in order to perform addition or subtraction, then the powers of the exponents of the two numbers should be same, but here not same. So we have to make it same by performing some shifting operation. So see here. So how we can make it exponent power 2 to 3. So actually it is the exponent value is 2, but we have to make it 3. So how we can make it 3? So by performing shift right operation on the matrix. Okay, so if you perform shift right operation, what will happen? So this 0, it will be shifted to the right, to the it will be shifted right side. That means the 0 will shifted to the after this decimal point. So that means we can represent y is equal to 0.0. So that means this 0 is shifted to the right side of the decimal point. Okay, so now we can write 0.0830. So this 4, it will be discarded in a shift right operation into 10 power 2. Previously 2 is there, exponent. So for every one shift right operation, the exponent value will be incremented by 1. So previously 2, now it will become 3. So this is a value of the second floating point number after performing shift right operation. Okay, so the x value is 0.9200 into 10 power 3, and y value will be 0.0830 into 10 power 3. So now the exponents of the two floating point numbers are equal or same. So now we can perform the addition or subtraction. So now we can perform addition or subtraction on matrices. Suppose if you perform addition, then you will get the value 1.00 30 into 10 power 3. Okay. So the x value will be 0.9200 into 10 power 3 and y value will be 0.083 into 10 power 3. So now we are going to add this. So since their powers are same, then you will get 10 power 3, 0, 3, 2 plus 8, 10. So you will get here. So 9 plus 1, 10. So here you will get. So this is the final sum value. 1.0030 into 10 power 3. So this is a final addition. Similarly, in the same way, we can also perform the subtraction. So if you perform the subtraction, then you will get the answer value 0.8370 into 10 power 3. So this is a subtraction. So when we are performing addition, so here we will get a 1. We are getting a 1 in this place. So we are getting 1 left side of the decimal point. So that means this is called overflow. So overflow. So that means it indicates that the resultant value it cannot store in a register. Okay. So that is that will be indicated by the overflow. So in order to rectify this overflow, then we have to perform a okay. So we have to perform a shift right operation. So if you perform a shift right operation, then see here. So this 1 will be shifted to the right side of the decimal point. So 1.003, because this 0 will be discarded. This 0 will be discarded in a right shift operation into 10 power. So we have performed the shift right operation. So for every shift right operation, the exponent value will be incremented by 1. So now it will become 4. Okay. So 0.1003 into 10 power 4. So this is a normalized result. So this is a normalized. So normalized means if before the decimal point, if we have a non-zero value, then that is a not normalized result, unnormalized result. Okay, so we have to make it normalized. Normalized means in the form of some 0.832 into 10 power 3, so like that. So we have to get the 0 before the decimal point. That is a normalized result. Okay. Similarly, when we have performed a subtraction operation, if we get 0.0837 into 10 power 3, so like that. So this 0, it is represents underflow. It represents underflow. So in order to overcome that, we have to perform a shift left operation. So by performing shift left operation, then the underflow problem can be rectified. Okay. So in this lecture, we have discussed about the pipelining concept, and also we have discussed about the arithmetic pipeline. So in arithmetic pipeline, we have seen how to perform the addition and subtraction on two floating point numbers. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.